This is the last section of 3.1, and we're going to be looking at a couple of diagrams, in particular a heating curve, a cooling curve, and a phase diagram. These are important diagrams that you will see on your MSL, so it's really important that you get practice identifying the different pieces and how to use them to predict different states of matter and the changes that matter undergoes. So the heating and cooling curves are diagrams that show how solids, liquids, and gases can change state when only temperature is changed. There's two really important sections on this curve that you need to be familiar with. The plateaus, which are the flattened regions. Those will represent the changes of state, such as freezing, melting, boiling, and condensation. And then the slopes, which will be the diagonal lines, which will represent the pure states of solid, liquid, and gas. Don't forget that the freezing point and the melting point are at the same temperature or plateau, and that boiling point and condensation point are also at the same temperature or plateau. This is your first look of a heating curve. Notice the temperature on the y-axis and the heat energy on the x-axis. As I increase heat energy to my substance, that causes the temperature of the substance to increase, and I can get the solid to warm to a liquid, the liquid to warm to a gas. We could also look at this as a cooling curve as well. If I remove heat energy, that would lower the temperature, and that would cause my gas to cool into a liquid, and then even cool more so into a solid. Let's focus in on the plateaus. Notice that these are where the phase changes are occurring. If I draw back the plateau lines to the y-axis, I can actually record the temperature at which that phase change is occurring. So for this first plateau, that would be our freezing point or melting point. And for the second plateau, that would be our boiling point or our condensation point. Energy takes two forms: kinetic energy, which is energy of motion, which is represented by temperature, and potential energy, which is stored energy. At the plateaus, since temperature is not changing anywhere along that flattened line, we would say that kinetic energy is constant. However, the stored energy, which is the potential energy of the substance, will be changing at this point in time. If we focus in on the sloped portions of the line, you will notice that this is where the pure solid, the pure liquid, and the pure gas exist. Notice now that any point along this line will show a temperature change. Thus, kinetic energy is changing, and this time the potential energy of the substance is staying constant. I know this is a heating curve for water because if I draw back the second plateau line to the temperature axis, I can record a boiling point of 100 degrees Celsius, and the first plateau line can be drawn back to record a freezing point of 0 degrees Celsius, which matches water. Let's talk about the process of changing state. We know that solid particles are very defined, very closely packed, very strong attractive forces. So as I add heat to the process, what's happening is I'm increasing the motions of the molecules so that eventually they can break free of their attractive forces. It's not until I get to this first point on the plateau line that the attractive forces are going to start to separate. So we have to get to a minimum amount of energy in order for this process to occur. And all along the phase change line, we will get solid to convert into liquid. So we say that the solid and the liquid are in equilibrium with each other. It's not until we get to this last point on this first plateau that the last solid particle will completely convert into liquid. We're still adding heat, so now that heat energy is moving into the substance to cause the motions of the molecules to move faster so that they can reach their second minimum point, which will be the boiling point. At that point, the first liquid particle will convert to gas, and all throughout this process, both liquid and gas will be in equilibrium with each other. And it's not to the last point on this line that the last liquid particle will convert to gas, leaving us then with only gas, and as we are still applying heat, that will cause the temperature of the gas to rise. Now this is important in terms of understanding that gases can actually have a higher temperature than boiling point. And that leads us to something very serious called steam burns. And you'll notice that during the process of boiling, the boiling point is 100 degrees Celsius. But if you look at any of the temperatures along this sloped line, you can see that they're a lot greater than 100 degrees Celsius. And we talked a little bit about thermal energy. The higher in magnitude that temperature is, the more thermal energy and the more danger it has. So steam burns are very dangerous because there's more heat content associated with that vapor or that gas. Let's see the type of questions that you will be asked when looking at a heating curve. First thing I would do is label this, and so I'm going to start by looking at my slopes and label the solid, the liquid, and the gas as A, C, and E. And then remember that at the plateaus you do have the combination of the two states because they are in the process of changing into one another. So the first question says, what is the boiling point of the substance? Since I know boiling is the conversion of a liquid to a gas, I'm going to direct my attention to the plateau where the liquid and the gas are together. And I will just draw that line back, and you can see it reads 100 degrees Celsius. Some students want to put down D as the answer, but that is not correct. I'm asking for a point. A point is a temperature. Do not give me a letter choice unless it's representing a physical temperature. Example 2 says, what letter represents the solid state only? Well, we pretty much answered that already. If we come down here to where there's only solid, you'll see that the letter that matches to that is A. This is an example of a cooling curve. I'm going to start off by labeling the slopes. Gas at the top, liquid in the middle, solid at the bottom. Remember that gases will always be in the upper area of the graph, solids will always be in the lower areas. And I'm also going to label the plateaus. This would be the gas and liquid plateau, and this would be the liquid and the solid plateau. So let's look at the question. It says, while the substance is cooling during the liquid phase, the average kinetic energy of the molecules of the substance does what? So we're going to focus in on the liquid phase, and we'll just pick a couple of points along the line, like 3. And if I draw those lines back, you will see that the temperature is decreasing. Since temperature is a measure of the kinetic energy of the substance, since the temperature is changing, the kinetic energy is going to change as well, and so we would say that it is decreasing. Our next question asks, what is the freezing point of the substance? Well, I know freezing point would be a temperature, and it's the process of a liquid converting to a solid. So I'm definitely going to go to the process of freezing, which is that lower plateau line, and I'm just going to follow that back, and I would record 70 degrees Celsius as my answer. The next question says, well, how long does it take for the gas to completely liquefy? Well, I know this is pure gas up here, and this is pure liquid. So I'm really looking at this point right here. The gas is in the process of changing over to a liquid. It starts off at the 2-minute mark, and it ends at the 9-minute mark. And so if I subtract those two numbers, it will tell me that that process took 7 minutes to occur. There's a second diagram out there that shows how solids, liquids, and gases can change state as both temperature and pressure are changed. These are called phase diagrams. A couple of very important points real quickly is that when you cross a line between states, that's actually going to determine the change of state, boiling, melting, freezing, condensation, and that a point directly on the line will identify the pressure and the temperature of a phase change. And what that's going to basically correlate to is the boiling point or the melting point of the substance. There are two important points on the phase diagram that you will need to be able to recognize. The first is the triple point, and the triple point is a temperature and pressure where all three of the states will coexist with each other. The second is the critical point, and the critical point is the temperature and pressure at which a gas can no longer liquefy. In the next slide, I will show you where both these points are and talk about them in a little bit more detail. This is your first look at a phase diagram. I want to point out to you that your solid is located on the far left, the liquid is in the middle, and the gaseous region will always be on the far right. I also want to go ahead and just re-emphasize this line, and that's the line that separates the solid from the liquid. As I cross over from a solid to a liquid, I'm actually going through the process of melting, whereas if I go in the reverse direction, I would be going through the process of freezing. I'm going to go ahead and just highlight this second line right here, which separates the liquid from the gas. And once again, if I cross over the line as I go from liquid to a gas, that's boiling or vaporization. From a gas to a liquid is condensation. And lastly, there's a third line I can draw, and that's going to be the line that separates the solid from the gas. And if we cross over that line, we're going to sublime. And if we go from a gas to a solid, that is the process of deposition. All right, now, where these three lines intersect is called the triple point. Notice that there is only one pressure and one temperature designation. I also want to point out the critical point, which is in the upper top portion of the liquid gas line. Remember that critical point is the temperature and pressure at which a gas can no longer liquefy. So basically, any temperature or pressure in this quadrant right here would be too high to get the molecules to slow down in order for their attractive forces to start taking hold of each other and turn into a liquid. On the last slide, I did mention that if you are to find a point on the line, that will be the pressure and the temperature of the phase change. This line right here is between the solid and the liquid. So anywhere on that line, we could record the temperature of melting point or freezing point. We can do the same over in this area right here. If I happen to have picked this point, I could go back and record the pressure, and this time the temperature, which would be the boiling point or the condensation point of that phase change. Let's compare the phase diagrams of water on the left and carbon dioxide on the right. If I was to go to standard pressure at sea level, which is 1 atm, and I was to go to the first intersection and drop down, I would record 0 degrees Celsius, and that would be my freezing point or my melting point. If I continued on and dropped down, I could record the boiling point or the condensation point of water. I can also highlight the critical point, which would be at 218 atmospheres and 374 degrees Celsius, and the triple point, which would occur when the pressure was 4.58 torr and the temperature was 0.0098 degrees Celsius. I could get both the solid, liquid, and gas to all exist within the same tube. Notice that this line has a negative slope. Water is actually one of the only substances where you will actually see the slope of this line in a negative direction. The reason for this has to do with the hydrogen bonding that holds the water molecules together. We can use the phase diagram to compare densities between the different states. If I picked a point, say about right here, and I proceeded to increase the pressure while keeping temperature constant, you will notice that I will start off in the gas phase. I will then enter the solid phase, and finally entering the liquid phase. What that tells us is the liquid state is the most dense, then the solid, and then the gaseous state. Remember, pressure is moving particles closer together, having collisions with those gas particles. So as the particles are being compressed closer and closer together, we get these different densities. On the other side, we have the carbon dioxide phase diagram. And if I start off where I originally was in the first diagram, I went to 1 atm, which is standard pressure. You will notice that I'm never going to get my solid to convert to a liquid. What's actually going to happen is the solid is going to convert to a gas, and that's called the process of sublimation. If I want solid carbon dioxide to actually liquefy, if I want to see the boiling point, I would have to actually raise my pressure up considerably. So let's say I'm at about 50 atmospheres of pressure. If at 50 atmospheres of pressure I start raising the temperature, I can get solid carbon dioxide to actually liquefy, and then I can actually get it to go into gaseous form. Notice the triple point. The triple point is at 5.11 atmospheres and negative 56.4 degrees Celsius. Once again, that's where I would see solid, liquid, and gaseous carbon dioxide all exist within a tube. I also have my critical point, which would be about 73 atmospheres of pressure and about 31.1 degrees Celsius. Notice that the slope here is a positive slope. Most substances will take on this positive slope in this region. And I can do the same thing I did before. I'm going to go ahead and pick a point on this graph. This time I'm going to pick about right here. And as I increase pressure while keeping temperature constant, you will notice I start off in the gaseous phase, and then I compress into a liquid, and then into a solid. Most substances will have their solid as their most dense state, then liquid, then gas, as seen using this phase diagram. Let's look at a series of questions that you can answer using the phase diagram. The first question wants you to determine the temperature of line B at 1 atmosphere of pressure. So if I find 1 atmosphere on my graph, and I move until I get to that first line, which is the line of freezing, it is the line that separates the solid from the liquid state, I can then drop down and record the freezing point, which is 273 Kelvin. The next question wants you to determine the temperature of line C at 1 atmosphere, but this time we're going to be looking at the boiling point, because I'm not going to stop at the first line, I'm going to stop at the second line. This is the line of vaporization or condensation, and you'll notice that it separates the liquid from the gaseous state. I'm going to do the same thing. I'm going to drop down, and I'm going to record its temperature of 373 Kelvin. They would like for you to identify point D, and hopefully you will identify that as the triple point. This is the temperature and pressure in which the solid, liquid, and gaseous phase all coexist. Point E is going to be your critical point. Basically what that means is any temperature above 647 Kelvin and any pressure above 374 atmospheres will not allow a gas to liquefy. The next question says, what change of state happens when you cross line B at a constant pressure of 10 atmospheres and increasing temperature? So I'm going to go ahead and just kind of estimate where 10 atmospheres might be, and I'm going to start to move across because I'm increasing my temperature. You'll see that I'm basically moving from a solid to a liquid, and that is the phase change of melting. The next one says, what change of state occurs when you cross line A at constant pressure of 0.001 atmospheres? So once again, I'm going to find that, and I'm going to cross line A. Obviously, I'm increasing my temperature here. I'm going from a solid to a gas, which is the process of sublimation. And the last question says, what change of state happens when you cross line C at 400 Kelvin to 300 Kelvin at approximately 5 atmospheres? So I'm going to go ahead and find 5 atmospheres, which is about right here. I'm going to find 400 Kelvin, which is right here. It looks like that's going to intersect about right here. And so as I am moving to 300 Kelvin, you will see that I'm crossing over the line from a gas to a liquid, which is the process of condensation. All right, this concludes section 3.1, where we looked at the different states of matter, how we can convert or interchange between the different states, and how we can use diagrams to show those changes. Once again, we will have lots and lots of practice in class working with these diagrams, and you will see them on the MSL come the end of the year. And these are two that definitely show up, so we want to be ready for them. Have a great day.